Hi guys, it's me again, and I'm going to discuss a very interesting and one of the most requested topic in CE, in civil engineering, which is the Mohr's Circle. When you say Mohr Circle, it is just a part of a bigger topic, which is what we call the transformation of plane stresses. But before we understand what is the Mohr Circle, let me introduce to you first the concept of stress elements. When you say stress element, it is a representation of a state of stress happening on a very small portion of a certain body upon the application of different type of forces. So like this. So this is just an example. It can be a beam or anybody that has a force in it, or torque, or whatever load you want to put it there. What are the things that you can see in the stress element? In the stress element, you can see normal stresses. These are type of stress that is acting perpendicular to the plane. And of course, for shear stress, these are the stress acting parallel to the planes. What is the general purpose of the Mohr Circle? The general purpose of the Mohr Circle is to determine the normal and shearing stress at any plane on a stress element. So meaning to say, if a certain element is subjected to normal and shearing stresses as shown like this one, if I want to get the normal and shearing stress acting on this particular plane, I can use the Mohr Circle. But if you are reading some textbooks, there is another way to perform this, and that is by using the transformation equation. But here is the problem with the transformation equation. You really have to memorize this very long and tedious formula. And you're going to use the formal notation and sign convention for normal and shear stress, especially when it comes to shear stress. The notation and the sign convention is a little bit complicated than the normal stress because there are two letters in which you should know in which the stress is acting to and in what direction it is pointing to. Some people might find difficulty in using this equation. That's why they opt to use the Mohr Circle. When it comes to Mohr Circle, there is an alternative notation for this. Take note, I will make this clear. The sign convention, especially for shear, that you are using in the Mohr Circle is different from the transformation equation. In this video, I'm going to introduce to you an alternative notation and sign convention for the Mohr Circle, which is informal but yet very easy to understand. Let me tell you this thing. I'm going to divide it into two. We have a sign convention for structural and we have a sign convention for geotechnical. Because if we are studying structural engineering, we are talking to materials that can be expressed in tensile and you can have a compressive stress in it. Unlike in geotechnical, in which the soil cannot have a tensile stress, it is only stressed appreciably by a compressive stress. How do this notation works? Say for example, this is the stress element. To easily solve some problems regarding this, I'm going to name the plane on whatever naming I want. I can put letters, numbers, whatever, a segment, any way you want. You can just name the plane on the most convenient way for you to do it. Say for example, this is plane A, this is plane letter B. These are normal stresses because it acts perpendicular to the plane. So we're going to use the lowercase sigma for the convention for normal stresses. Same thing for formal sign convention, the one I've shown you in the transformation equation. And look at the subscript. The subscript tells you in which plane it is acting. This arrow is acting perpendicular to plane letter A. That's why I'm going to put this sigma sub A. And for this one, so this should be sigma sub B. The normal stress is positive if it is tension. We all know that that is the conventional designation for normal stress. If it is tension, it should be positive because it creates a positive deformation, which is elongation in strand of materials. And of course, if the normal stress is negative, we're going to tag it as compression. And how about for shear? Let's say, for example, these are the stress elements. This is not the formal way of writing the symbol for shear stress, but this is very practical and easy to understand. For notation, this is the lowercase tau, and the subscript tells you in which plane it is acting. So, for example, this shear stress is acting on plane A. That's why I'm going to put tau A over here. And shear stress is plotted positive in the Mohr circle if the shear stress tends to rotate the element clockwise. Tau A tends to rotate this one clockwise. Therefore, if I'm going to plot the Mohr circle for this state of stress, I'm going to mark it as a positive value. Tau B, it is tending the body clockwise. So I should put positive sign. Shear stress is plotted negative if the shear stress tends to rotate the element counterclockwise. Let us discuss some important facts about stress element. Number 1, parallel planes have equal normal and shear stress. For example, in this plane, you have a 10 megapascal normal stress and you have a shear stress of 8 megapascal, in which the normal stress is tension, 10 megapascal, and the shear stress, 8 megapascal, tends to rotate the body clockwise. What do this statement mean? This plane is parallel to this one. Therefore, basically, if you want to know what is the normal and shearing stresses, it is shear stress over here. It is automatically 10 megapascal tension and 8 megapascal. So the 8 megapascals should also rotate the body clockwise. Same for this. And so, if I'm going to cut any plane parallel to this plane, like this plane is parallel to this one, so this plane will also have the same normal stress and the same shear stress. So meaning to say, if you name it as plane A, all planes that are parallel to this should also be named as plane letter A. Another idea, shear stresses on perpendicular planes are equal in magnitude but opposite in the direction of rotation. What does this mean? This plane has 8 megapascal shear, which tends to rotate the body clockwise. So therefore, if you're going to analyze any plane that is perpendicular to this plane, it should have also a shear stress which is the same magnitude. So in our example, it should be 8 megapascal, but it should rotate on a different direction. The reason for this is we have this to satisfy the condition of equilibrium of rotation. Number 3, unlike shear stress, normal stress on perpendicular planes are independent to each other. For example, this is 10 megapascal. The perpendicular plane, like this one, can have any values it can. Say, for example, this is 10. It does not necessarily follow that if this is 10, this should also be 10 megapascal. You can have any values for it. You want to make it 15. You want to put a 15 megapascal normal stress over here. You can. But in shear, take note, you cannot do that. If this is 8, this should also be 8. If there is no shear stress here, there should be no shear stress also here. And of course, to understand how the Mohr circle works, you should have a specific problem. For the stress element as shown, determine the major and minor principal stress. Number 2, determine the orientation of principal planes. Number 3, determine the maximum shear stress. And number 4, determine the normal and shear stress on the 30-degree plane as shown in the figure. To solve it in detail, I'm going to solve it in our whiteboard. So here is our drawing. How are you going to solve the question? So to be able to solve all of that problem, you should construct first the Mohr circle. But the question is, how are you going to construct the Mohr circle? So the first thing that you should do is create a Cartesian coordinate system. Of course, you know this from analytic geometry. You have the x and the y-axis. So let me draw it. This is your coordinate system. The x-axis will correspond to the normal stresses. So let me call it sigma. And the y-axis corresponds to shear stress or symbolized by tau. To make it simple, here are the steps in doing this. You put a name on planes. So whatever you want it to be, it depends on you how you name the plane. So say for example, this plane, I can name it as plane letter A. And then this one will be named as plane letter B. So this plane and this plane, we don't need to name it because as I said a while ago, all parallel planes are the same. So meaning this one is also plane B and this one is also plane B. They have the same details of normal and shearing stress. And then you're going to make all the stresses as a coordinate. So since the normal stress is the x-axis and the y-axis is the shearing stress, therefore, you're going to designate the normal stress as the abscissa and this one is the ordinate or the y coordinate. For plane letter A, so since this is tension, this is positive 60, since this 10 megapascal tends to rotate the body counterclockwise, therefore we're going to designate it as negative 10. And for letter B, of course, since that is also tension, so we're going to put it 80 as your x coordinate, and this one is positive 10. You're going to plot these coordinates on this coordinate system. So the way you do it in analytic geometry, as simple as that. So 60 negative 10 is, let us just approximate it because my hands are not perfect. This is 60 negative 10. And let us say this is letter A. This point is letter B. Say this is 80 and positive 10. What is the next step? Let me remind you. Check first if those coordinates are coming from the plane that is perpendicular to each other. Say this is plane A and this is plane B. As you can see, it is a 90 degree or perpendicular to each other. So that is by default. So if you are given a stress block, so automatically you just assume it as a 90 degrees. Unless otherwise, the problem is state the exact angle of this one. Since there is no angle, it is assumed that this is perpendicular to each other. So therefore, if this coordinate came from the plane that is perpendicular to each other, you can say that this is now the diameter of our Mohr circle. Let us connect points A and B. And here is your diameter. So since negative 10 and positive 10 are equal in magnitude, so therefore, the x-intercept will serve as the center of the Mohr's circle. I just do it in freehand, so I'm apologize for that bad figure. But anyway, let us just consider it that this is a perfect circle. How are you going to interpret this? All coordinates on the circumference of the Mohr circle represents a stress on a certain plane in our stress block. So look at this. This point has a coordinate of 60 negative 10, and it represents the stress on plane A here in our stress block. The first question is, determine the major and minor principal stresses. So when you say principal stresses, these are the extreme values of normal stresses. When you say principal stresses, these are the values of sigma max and sigma min. So therefore, class, if you're going to look on our Mohr circle, it is very obvious that the coordinate of the Mohr circle with the highest sigma is this one. Let us put a red dot here. So therefore, this will be our sigma max. And the coordinate on the Mohr circle that has the lowest value of normal stress is this one. These are the extremities. This coordinate is what we call the major principal stress, and the other one is the minor principal stress. And if you're going to look on our Mohr circle, it is very, very obvious to take note that the corresponding shearing stress on the major principal stresses is equal to 0. So meaning to say, another definition of the principal stresses, it is the stress in which the corresponding shearing stress is equal to 0. Let us get it using conventional geometry. To determine the coordinate of this center, you just take the average of 60 and 80. So that is equal to 70. This is 70, 0. And to get the value of sigma max, you just add the length of the radius. So if you're going to do it manually, geometrically, you can construct a right triangle like this one. This is 80 and this is 70. So therefore, this is 10 megapascal. And this one is also 10. And by Pythagorean theorem, we can get the value of R. Of course, that is R is equal to square root of 10 square plus 10 square. That is equal to 14.142 megapascal. Let me put this here. 14.142 megapascal. So, if you want to get the value of sigma max, you just add 70 plus 14.142 megapascal. And the answer is equal to 84.142 megapascal. And for the value of the minimum normal stress is simply 70 minus 14.142. Of course, if you want to get the coordinate of this one, you just subtract the length of the radius. Okay? So 70 minus 14.142 is equal to 55.858 megapascal. So these are the values of maximum and minimum normal stresses. Before we continue, let me clear this thing. In the topic of transformation of plane stress, the major and the minor principal stresses should be considered algebraically. What does it mean? Say, for example, you have this Mohr circle, and then the coordinates of this one, say, for example, this is 2 megapascal, this is negative 8 megapascal. So technically speaking, when we talk of the absolute value of the values of the normal stresses, it is very, very clear that 8 megapascal has a higher absolute value. But guys, since you're going to consider it algebraically, 2 megapascal is still considered our sigma max there. This one will serve as the sigma mean. So you always consider the sign. So you just interpret it practically based on the requirement of the problem. For example, this is your Mohr circle, and then the problem asks you, what is the greatest compressive stress? You should answer me 8 megapascal. So I hope that's clear. So this is just a mathematical designation. Okay, that sigma max is always on the right and sigma mean is always on the left side of your Mohr's circle. The next question is to determine the orientation of the principal plane. So we're going to locate in which plane the major and minor principal stress exist. I'm going to explain to you a simplified way of interpreting the Mohr circle. The radius of the Mohr circle can represent a plane on the state of stress. Like this, for example, this is a radius, and look at this. If the radius is pointing to a certain coordinate, for example, 80-10, this radius will represent a plane in which the stress is 80 and positive 10. So by obvious reason, this radius is representing plane letter B. And this radius is representing plane A. If you want to know where's the plane that contains the major principal stress, look at this radius. This radius is pointing to the coordinate with the highest value of sigma. Let us make a name on this radius. Let us say this is MAJ. So stands for major principal stress or so meaning to say this radius is representing the major principal plane. When you say major principal plane, that is the plane that contains the major principal stress. You have to have reference plane first. You can have it here or you can have it here, depending on you. So, since this R is nearer to this radius, therefore, we can just use it. Guys, without the greatest knowledge of trigonometry, if this is 10 and this is 10, this angle is 45 degrees. If plane B is your reference and you're locating the major principal stress, just look how are you going to rotate from your reference plane. For you to come up with the major principal plane, you have to rotate by this direction. And this direction is clockwise. Clockwise from radius B. So this is the idea. The angular distance in the state of stress is always twice in the Mohr circle. So meaning to say, if you're going to put the distance of orientation of angles in the Mohr circle to the state of stress, you're going to reduce it to half. From plane B, to get to major principal plane, you have to rotate clockwise by 45 degrees. Let me erase this first. So using plane B, from plane B, you're going to rotate also by clockwise, but not by 45, but by half of it. So 45 over 2, that is 22.5. Meaning to say, from here, angle 22.5 clockwise. This plane contains the major principal stress. So what does it mean? So if I'm going to cut it and show the free body diagrams, so if I'm going to expose what are the values of stresses here, this one is 84.142 megapascal. And this one is also, of course, 84.142 megapascal. And on this plane, there is no shearing stress because the y-ordinate is 0. In this plane experiences the greatest value of the normal stress. And you want also to get where is the minor principal plane. This radius is the one pointing to the sigma mean. Meaning to say, from major going to minor principal stress, that is 180-degree rotation. So if you're going to transfer that 180-degree rotation in the state of stress, it will be just half. If this is the major principal stress, anything that is perpendicular to the major principal plane contains the minor principal stresses. Remember, if you want to consider those 2 points as a coordinate, you should check first if this is really 90 degrees. Why? Because 90 times 2 is 180 and 180 is a straight line. So like this is major and this is minor. This is 180 degrees to each other. Therefore, if you're going to transfer it in our state of stress, it is perpendicular to each other. If this is 22.5, you can just get the orientation of this one geometrically. Determine the maximum shearing stress. If you are just considering the two-dimensional analysis of the Mohr circle, you are just getting the maximum in-plane shear stress. Look at the coordinate of the Mohr circle with the highest value of the y-ordinate. So it's basically this one. And this is equal to the length of the radius. Therefore, tau max is simply equal to 14.142 megapascal. So if you want to know in which plane this tau max is existing, you can do the same thing. So say for example, your reference is plane B. Of course, if this is 45, this one is also 45 degree. From plane B, you can rotate by counterclockwise 45 degree. Here is your plane B. Sorry, I erased B and A. So you're going to rotate by counterclockwise 45 degrees. So you can just put it here, and this is 45 degrees. So meaning to say, this plane experiences the maximum shearing stress in plane. Meaning, if I'm going to cut again the free body diagram of this one, if this is positive, 14.142, okay, this is the coordinate, the y coordinate here is positive 14.142. So meaning, if that is positive, the direction of the chair should tend to rotate the body clockwise. So therefore, 14.142 shearing stress should act in this direction to rotate the body clockwise. And of course, in this free body diagram, the application is like this one. Next, number 4. Determine the normal and shear stress on the 30-degree plane. Let us just get it back here. Basically, guys, you just name it as A. How are you going to determine the normal and shear stress here? As I said a while ago, the radius on the Mohr circle represent a plane on the state of stress. Meaning to say, we will just locate what radius on the Mohr circle represents this plane. Let us put a name on this plane. Let me say that this is plane letter C. You should have a reference plane first. Okay, it's up to you. It depends. You can use this plane B as your reference plane, and you can also use plane A as your reference plane. So I want to use the reference B as my reference plane. If you want to go from plane B going to plane C, you have to rotate by this amount. And since this is 30, of course this is 90, this one is 60 degrees. So, from plane B, you have to rotate by clockwise from B. So, here is your B. From B, you're going to rotate also by clockwise, but you have to multiply it by 2. So, from letter B, it is very obvious that the radius will fall on this side. From plane B, you're going to rotate by clockwise 120 degrees. So, therefore, this radius is representing the plane C. and the coordinate in which it points to the circumference of the Mohr circle is known as sigma c and tau sub c. To solve that geometrically, guys, you should have the angle between this radius and the x-axis, which is 120 minus 45. 75 degrees, meaning the radius that represents plane C is 75 degree clockwise from the positive x-axis. Are we going to arrive on the same radius if you're going to use A as your reference plane? Yes, of course. Guys, this is A. And as you can see, plane A is not directly connected on plane letter C. What you're going to do? Okay, as I said a while ago, all parallel planes are equal. So you connect it here and construct a plane parallel to this plane. So this is also plane letter A. So if this is 30, by alternate interior angle theorem in mathematics, this is also 30 degrees. Meaning to say, from plane letter A, you have to rotate by counterclockwise 30. So if you are going to rotate counterclockwise, 60, because you have to multiply it by 2. If this is 60, and of course, this is 45. If this is 45 and 60, and if you want to get this angle, the answer is still 75 degrees. So you arrive on the same radius that represents the plane letter C. If you want now to get the coordinate, you can just create a right triangle like this one. So this is just an illustration. To get the normal stress on C, the coordinate of the center, you just add the length of this leg. The radius is 14.142. This is 14.142. And this one is 75 degrees. If you want to get this length, that's 14.142 times cosine of 75. This is equal to 3.66. And this one is simply 14.142 sine of 75. 13.66 megapascal. So, let us interpret the result. To get the sigma C, that is just 70, plus the length of the leg, which is 3.66. This is 73.66 megapascal. That is 73.66. And for tau C, since it is plotted below the x-axis, so therefore we can just name it as negative 13.66. So it means, if you're going to expose or cut this one on the 30-degree planes, you can have any FBDs. This is 73.66. It follows that this plane experiences a normal tensile stress of 73.66 megapascal. And guys, this is negative 13.66, meaning plus, in our sign convention, I told you that negative shear tends to rotate the body counterclockwise. So you should apply it in this direction so that the effect is counterclockwise. So the direction of shear happening on this plane is 13.66 megapascal. So from Newton's third law, if this is 73.66, this is in this direction, 73.66, and the shear is going in this direction, which has a value of 13.66 megapascal. As you can see, if you're going to transfer the shear stress on this FBD, the effect of shear stress is also counterclockwise. That proves that our answer is really correct. I hope guys you understand how to interpret simply the Mohr circle. On my next video, I'm going to show you a calculator technique to determine all of this without doing some tedious geometrical solution. Just tune in and don't forget to subscribe for more learning videos about engineering. Goodbye guys. Wait for my next video.